In this video, I'm going to go through some examples of calculations with linear equations. So a linear equation is an equation with the form y equals ax plus b, and it's intuitive to understand this in a graphical form. So in graphical form, we think of x as the input variable along the horizontal axis, and y is the output variable, and that's on the vertical axis. And then this linear equation, y equals ax plus b, can be represented as this straight line, this red line here, that in this particular example has an upward slope. And the slope of that line, which we would calculate by finding the rise over the run, that ratio is constant because this is a straight line. So if we just picked 2 points along the line, the rise would be the difference in the y values between this point and this point, so how much it's risen, and then the run is the difference between the x values for those 2 points, so how much the x has increased between this point and this point. And if we calculate that ratio, rise divided by run, we get a number that would be the same no matter where along the line we calculated the rise over the run. And that number is the slope, which in this equation is given by the letter A. And B is typically just called the intercept, but more specifically it's the y-intercept when x is 0. So on this diagram that I've drawn here, I've got x equals 0 on the left of the graph where the y-axis crosses, and so the y value on the line at that x value of 0 is the y-intercept, and that's given by the letter b in this equation. So y equals ax plus b, and this is the slope-intercept form of the line. Sometimes you'll see a line represented in a different form known as the point-slope form, and this is equivalent to the slope-intercept form, it's just written in a slightly different way. So to find the point-slope form of an equation of a straight line, we just pick any point along the line. And so I'm going to represent that here with x0 and y0. So any point along the line, so here for example, so the x value would be whatever the horizontal axis value is, and the y value would be whatever the vertical axis is. And we're going to call the horizontal axis value x0 and the vertical axis value y0. So these are just two numbers, and then the point slope form has y minus y0 on one side of the equation. So y is the variable and y0 is a number, and that's equal to, on the right side of the equation, the slope a times the difference between x and x0. So x is the variable, x0 is just a number. And we can see that this is equivalent because if I just rearrange this equation slightly, so let's move y0 to the other side of the equation, and let's expand this expression here. So we've got a times x, and then let's write down the y0 that we've moved to the other side, and then we're going to have minus a times x0. And remember, y0 and x0 are just numbers, and a is just a number, it's the slope. So this part of the equation, y0 minus a x0, is just a number. So our equation looks like y equals a times x plus a number. And that's the same as the slope-intercept form, y equals a times x plus a number. So this gives us one way of calculating the intercept if we know the point-slope form of the equation, and we just rearrange it like this, then we know that the intercept would be y0 minus a times x0. So that gives us a way of going back and forth between these two equations. Sometimes it's more useful to have the equation in the point-slope form, sometimes it's more useful to have it in the slope-intercept form. And this just gives us a way of going back and forth. But let's use the slope-intercept form to solve some example problems. So for example, let's suppose that we have a slope of 20 and an intercept of 50. And this is going to represent a cost function. So we're doing a financial application here, and instead of the letter y, I'm going to use the letter c because this equation is going to allow me to calculate costs. So we're going to have ax plus b, so a is 20, and then x here represents the number of units that we're thinking about for this particular cost function. So it might be a count of some product that we're manufacturing, say. And then we add on b, that's the y-intercept, or the c-intercept in this case. So this is our cost function, and so we can use that cost function to figure out what the cost would be for certain inputs. So let's suppose our value of x is 10, then we can just plug in the value of 10 here, and we'd have 20 times 10, which is 200, and then plus 50, so we'd have 250 for our cost. So the cost to produce 10 items is, let's say, $250. If we want to produce 30, then we plug in 30 for the value x, and 20 times 30 is 600, plus 50 would be 650. So it's straightforward to plug in different values of x to figure out what the cost is, the output. Let's do another example. Let's suppose now a is 22 and b is 0. So now this is going to represent a revenue function. So we're selling our items for $22 each, and so the revenue that we get is just going to be 22 times the number of units that we sell. So this one's pretty straightforward. If I sell 10, I would make $220. If I sold 30, I would make $660. Let's think about profits now. So profits are going to be the difference between revenue and cost. So I could think of a profit function, which is going to be the revenue function minus the cost function. So the revenue function was 22x. The cost function is 20x plus 50. And if I simplify that, I'll have 22x minus 20x, so I'll have 2x, and then minus 50. And again, we could see what the profit looks like for different inputs x. So for example, if I'm producing 10 units, my profit would be 2 times 10 is 20, minus 50 would be minus 30. And we can see that from our earlier calculations. Our revenue was $220 and our cost was $250, so we've actually lost $30 if we produce 10 units. If we produce 30 though, we're going to have 2 times 30 is 60 minus 50 is 10. We're going to make a profit of 10. And we can see that because we had revenue of 660 and cost of 650, so we made a $10 profit. This might raise the question, what value of x would give us a profit of 0? So what's the break-even point? So what is x when p equals 0? Okay, so now we're taking our profit function to x minus 50, and we're setting that equal to 0, and then we're solving for x. So I'll just do this in stages. 2x equals 50, so x equals 50 divided by 2. So when x is 25, we're going to break even. And we could just check that. If we plug in 25 into our profit function, we'll get 2 times 25 is 50, minus 50 is 0. So we break even for x equals 25. But we probably want to make a profit. So let's suppose our profit target is 20. What would x have to be to produce a profit of 20? So now we just set 2x minus 50 equals to 20. So now we're going to have 2x. If I move the 50 to the other side, I'll have 70. So now x is 70 divided by 2, so that's 35. And we can just double check by plugging 35 into our profit function. 2 times 35 is 70, minus 50 is 20. So x equals 35 does give us a profit of 20. Sorry. So that's a few examples of using linear equations to solve some problems.